All right, ladies and gentlemen, welcome back. I think I've reset the class from last day to now, and so I just want to jump right in and remind myself that, as it was mentioned to me, we forgot to finish off this problem. So if anyone wants to type into the chat their answer, their reaction order with respect to A, or speak it out loud, and the overall reaction order, that would be much appreciated. Anyone have an answer for that? I do want to point out that someone did ask me a question. I'm not sure if it was in this class or the other class. And okay, Afrin got overall 2. Yeah, you aren't going to get a number that's close to 2 for the reaction order with respect to A. And that clearly is my fault. It ends up being 2.29, which should either round to 2.5 or to 2. That's my fault with the numbers, and yeah, I apologize for that. But yes, if Ali got 2.3, which needs to round to integer or half integer, and this one is, well, of course, manufactured data, and somehow that 20 should be a 16, and then you're going to get the right answer. Anyway, 2.3 is the reaction order with regards to A, and plus, because the reaction order with respect to B is 0, the overall reaction order is also 2. Good deal. Before we continue with the course material, I want to set up for a demonstration. So let me just go do a few things. So what we have here are a bunch of glow sticks bought at the dollar store and different colors. And if you are unfamiliar with these, they have inside of them a very thin glass tube that contains one chemical, and then the other chemical is in the outer area. And what I'm doing is I'm just breaking the glass tube. For all of these, and what you can see on the table is that they're starting to glow. So the chemical reaction that we have here gives off light. It is fluorescent. And we talked about those stars in your rooms that were phosphorescent. This is similar in the sense that a chemical reaction is now giving off light. And so what I have here now is a bunch, mix it up just a tiny bit, of glow sticks. In front of me there are 3 beakers, and the center one just has room temperature water in it. And I'm going to add ice to one of the beakers, and we'll let that cool down. And the last one, I'm going to put on a hot plate, and we're going to heat up. So the idea behind this is that we're going to very quickly later today, we're going to look at the temperature dependence of rate constant, or how temperature affects a reaction. And we're going to take these glow sticks that are at about 20 degrees right now in this room temperature water, and we're going to put them in hot water and in cold water and see how that affects the rate of reaction. So we will come back to that in just a few, half an hour or so. I also must admit that I am 1 USB connection short of what I need to do demonstrations. So I will have to flip a few pieces of equipment around next time we want to go back to that webcam. So please forgive me on that. Okay, so now while we're waiting for that to heat up, what we're going to do is we're going to go back and finish off the example that we were working on, if I can find it. Last day, we finished off by going through and determining the integrated rate equations and the half-lives for zeroth, first, and second order reactions. We realized that the linear relationship is different for zeroth, first, and second order reactions. And so by plotting, we should be able to figure out if a reaction is zeroth, first, and second order. Now, we're limited to what we test for. We could derive an integrated rate equation for a half order or for a -1 order or what, but the majority of chemical reactions are zeroth, first, and second order. So we looked at this example with regards to the dissolution, the association of sucrose, hydrolysis of sucrose in water. But then we were, at the end of the day, looking at this data, and that's where we finished off. We took, there we go. We took the data that we have here and just making sure you actually see this, good. We took this data and we were able to then, whether we worked in pressure or concentration, whatever, I just wanted to show the conversion to concentration. We tabulated the concentration, the natural log of the concentration, and 1 over the concentration. And by plotting, we were able to determine if something was zeroth order, and we did that graph down here, and apparently that's, there we go. In this zeroth order test, we plotted concentration versus time, and what we figured out was that it wasn't zeroth order because that's not a straight line. So we moved down and we now do a first order test. And just give me a second here. I actually want to make my grids just a tiny bit bigger so that I actually get reasonable spacing here. So time is still the x-axis, and now we're going to be plotting natural log of concentration. And so this would be 20, 40, 60, 70. And on the vertical axis, you need to look at the data, and what you find looking at the data is that it ranges from, around -3 to -8. So -3, 4, 5, yeah, -3, -5, -7. There we go. So there is our data that we now want to do our test for first order with. And at time 0, it is -3.4. At 20 seconds, it's 4.6. About right there. 40 seconds, it's 5.9. 60 seconds, it is -7.18. And 70 seconds, it's -7.75. And looking at this, I can't shut that off. Oh, yeah, and I can't draw a straight line either. you end up seeing something that looks about like that. That's a very good, even for this rough graph that we've created, that's a very reasonable first straight line relationship. So very likely it's first order. If you get this, you're done. You've answered the question and you've got a first order reaction. You would need to calculate the slope. I want to go through and just for completeness, do the second order as well. So while it is very likely first order, we are going to do the second order. You would not need to do this on an exam. As soon as you get the correct answer, you're done. But we're going to do a second order test. And this is now plotting 1 over the concentration. $20, $40, $60. And if we look at 1 over the concentration, the values range from about 30 to 2,300 or 0 to 2,500. 500, 2,000, this would be 1,000. And now when we plot this data, time 0 is about 30.6, 20 is 105, 40 is 370, it's about right there, 60 is 1,300, and 70 is 2,300. So this relationship is very clearly not a linear relationship, so it is not a second order progression, second order reaction. If anything else, this just confirms that it's not second order by plotting this. I want to go back to this first order test that we've done right here. And a couple things that I want to bring about or talk about is now what do we do with it? If we remember the equation, the slope is equal to negative the rate constant k. Now, if you were to plot this on graph paper and take the time to actually plot the values correctly, it should be no problem to go through and calculate the slope, which from the equation rise over run. As I mentioned last day, in first year, I expect you to be able to create graphs by hand. I expect you to be able to calculate the slope by hand from a graph. You'll be expected to do that on exams. If you know how to create a graph by hand, then when it comes time to doing it on computer, which is what's going to happen in all of your other chemistry classes, take analytical chemistry, and you will see you'll be using Excel. But in order to calculate a publication quality graph in Excel or any other graphing program, you need to do it by hand first. And that's what I want to get here. The title isn't the same as the axes labels and the like, as to how that graph goes together. Talk about more of that next, well, when you create graphs. When you calculate the slope, some of you have been taught to use data points, and that is generally a bad practice. If I look at the data points for what is presented here, only one of the data points might go through the line, and that's because in general they don't. This data is actually pretty good as presented, but if you start zooming in on this, you will find eventually places where it crosses exactly. So instead of using the data points, what you are looking for is locations where the line crosses the grid lines almost exactly or exactly. Now you have simple numbers, because of the way you set up your graph, to calculate the slope thereof. And see if I can find another one in this data set. And there's another one right there. Those would be the 2 points that you would use to calculate the slope, rise over run. Okay. Yes. So let's go here. What you would get, I'll get back to that slide in just a second, is if you were to actually plot them, which is what you get here, concentration versus time, which is the 0th order test, and clearly it's not a straight line. There's the best fit line going through. The 1st order test does give you a linear relationship, and the 2nd order test does not, as what we did by hand. What we do get out of this is that the slope is actually calculated for us, and the slope is negative 0.0626. So the slope minus k, oh sorry, I'll just put down, that's weird, is equal to negative 0.0626. The one thing that it doesn't give you is the units. The units you get from the equation of the axes. The rise is natural log of concentration. There's no units with natural logs. The x-axis is time, so it's 1 over the units of time, which in this case is seconds. So our rate constant k would be the positive of that value with units of 1 over seconds. Now, in the context of doing this by hand, you're probably not going to be able to get it accurate to 3 significant digits. I don't expect you to be able to do that, but if you were to do it, and you can go take this graph or regraph it and do it by hand, if you get anywhere from 0.06 to 0.060 to 0.065, that's acceptable. And what you'll find is that you should be able to get within that range very, very easily using very simple graph paper and graphing methods. And that's the practice. That is the expectation for graphing here. Does anyone have any questions?
Roy, I just have a question. Is your slope negative or positive? Because you have it, like the top is negative, but then k you said was positive. Is it supposed to be positive or can it be?
Well, no. Well, the slope of my line is negative because and that's kind of cool. I can do this. Because it is going downwards, my slope is negative. It's negative 0.0626. But if you have the equation of that we were using, the equation that we were using is natural log of k is natural log of, what is it? Equation? Concentration. Natural log of concentration is minus kt plus the natural log of the initial concentration. So here, we plug this in, we get y, m, x, and b. The slope is negative the rate constant k. So the slope is negative 0.0626, which is also equal to negative k, which makes k a positive value. Does that answer your question?
Yeah, I see it. Thank you.
All right, good. Are there any other questions on this? Okay. I do want to go up here and spend just a few seconds looking at this data table with this in mind. What are the significant figure rules when calculations involve logarithms? What are the sig fig rules when calculations involve logarithms? And I'll give you a few seconds to think about it for yourself. So take 10, 15 seconds, come up with an explanation for what are the sig fig rules involving logs. Go ahead. Give you 10 seconds. Anyone wish to offer their knowledge, recollection? Alex tells me it adds one further significant digit to the right. He's technically almost correct, but I'm not even saying that's a cheat way. It gives you the right answer, but it's not for the right reason. Why does it add one further significant digit or more? Anyone else? Going once? Come on. Someone's got something to say. Maybe? Ooh, that's not gonna work. Okay. All right. Well, let's, you consider the numbers to the right of the decimal. That is correct. Only the decimal places are significant. And we're getting close to, we're getting the answer. So I'm just going to go over here to there. Yep. And try to remember what logs actually mean. So I'm going to pick a number almost at random, but I happen to have what it is, and that number is 7531. It doesn't matter what number you pick, 7531 is, I actually at one point in time got students to just call out digits, and that's what we got. 7531 came up. And if we were to take the log of this value, you would get 3.8769. Now, this is the log base 10 because it makes the math easy. What can anyone, without touching your calculator, tell me what the log is of 753.1? What is the log of that value? While you're typing it into the chat or talking, what is the log of 75.31? Or 7.531? So I will guarantee you that the log of 753.1 is 2.8769. And of 75.31 is 1.8769. Of 7.531, it is 0.8769. And if I were to go 0.007531, I'm going to get negative 2.8769. That is to say that the number before the decimal point tells you the location of the decimal point. In the number. Okay? Tells you the location of the decimal point over here. Or the power to which the number would be raised. It's the power to which the number would be raised if you were to put it in scientific notation. The values after the decimal point are the significant digits. They represent the actual value of the number. So however many, to answer your question, and it follows along with what people are putting in the comments, however many significant digits there are here, okay, there's 4 significant digits there. There will be 4 digits after the decimal place. And similarly, if you have to go the other direction, you take 10 to this value. The number of digits after the decimal place is the number of significant digits in your final answer. What this means, we can get to our data, is here's the data we have. If you look at the table of concentration, which is this one right here, there was 3, 3, 2, 2, and 2 significant digits. If I take the natural log, or sorry, if I go over all the way over to the far side, I get 1 over the concentration. There's 3, 3, 2, 2, 2 significant digits. I've underlined the non-significant values there. But in the natural log, which is the next column, okay, there are 3 digits after the decimal point. 3 digits after the decimal point. I've still kept 3, but I've underlined the last one to give me 2 significant digits there. That is how significant digits translate into logarithm operations. Does anyone have any questions on that? All right, so that is it for the material in problem set 1. So you now have all of the knowledge to complete problem set 1, which means that there will be a quiz on problem set 1 coming up very, very soon. That would be next Monday. So between now and next Monday, you are going to have the opportunity to find the time to do problem set 1. You're free to work with each other. You're free to work with the TAs and the SIs. All of that is open. The quiz is going to be next Monday, Tuesday, and Wednesday. Whenever you start the quiz, you'll have, and I still never looked it up, 30 or 45 minutes or something like that. You'll have a fixed amount of time, and you have 1 attempt to do the quiz. The questions on the quiz are questions off the problem set with the numbers changed. So, or parts of those questions. So you'll be expected, if you've done the problem set, the quiz is going to be easy. If you haven't, you won't have enough time to do it. That is the incentivization to doing the problem set. And as I said, you work with whomever you want, teach each other, work with the TAs, because you need to learn it for the quiz. Of course, the quiz is done on your own, not done as a group or whatever. Are there any questions thus? Is it really 20 after? No, it's 12. Why do I have... Oh, now it's better. The clock on the wall seems to have stopped, so I was just a little scared. Is the quiz open book? Yes, because I can't stop you, honestly. So the question was, is the quiz open book? And yeah, I can't stop you, so might as well make it open book. We'll see. We'll see how you do. It's not going to help you much. Basically, you have the problem sets you've already done. The quiz is on yours. You can look back at that. That would be the best resource to have to solve the problem set quiz. All right. It's not heated up. I'm just looking at the demo, and it's not set up yet. So let's continue with this material. This is now starting the material that is in problem set 2. But still part of kinetics, we're going to look at factors affecting the rate constant. What's presented here is, what is presented here is the equation that we've already looked at. We have, at the very beginning of this section, we looked at the rate equation being 1 over the stoichiometric coefficient times the change in concentration over the change in time. That was proportional to the differential rate equation. We also noticed that the rate was some rate constant K times the concentrations raised to some powers, some reaction orders. We've already looked at the dependence of the stoichiometry on the stoichiometry and on the reaction concentration, A, B, C, D. What we're going to look at in this section is the factors that affect the rate constant K. Now, I don't care about dates. There won't be a question on an exam about dates, but just to let you know that this theory was developed in the 1880s by savant Arrhenius, and he discovered an empirical relationship between temperature and the rate constant. Empirical means that it fits the data. They didn't understand why, but they just knew that this equation, named the Arrhenius equation, gives you a relationship between temperature and the rate constant. Subsequent to this empirical relationship being discovered, the theories came up that started to explain it, but came afterwards. We have the Arrhenius equation, which tells you that K, which is a function of temperature, is equal to A times the e to the minus EA over RT, where A is the frequency factor, which is the frequency of reactants colliding with the correct orientation. This will make sense in a few slides. EA is the activation energy, the minimum energy required for a reaction to proceed. Again, this will make sense in a few slides. More sense in a few slides. Right now, what I want to do is I want to take the Arrhenius equation and I want to go through these examples. First, we're going to arrange the Arrhenius equation in a way that is suitable for plotting. Just give me 1 second here. There we go. And so let me just go over here. Okay. That's the other class. This is your class. So we want to rearrange the Arrhenius equation in a way that is suitable for plotting. Just to remind you, the Arrhenius equation is K AE to the minus EA over RT. What I want to do is I want to take the natural log of this entire thing. Just out of curiosity, because I'm going to do it very, very quickly, what is the expansion of the natural log of A times B? How does that expand?
1A plus 1B.
That equals natural log of A plus the natural log of B. Yes, good. Because that's what we're going to apply here pretty quickly. So this gives us natural log of K is equal to the natural log of A times the rest, natural log of A plus the natural log of the exponential cancels out, plus negative EA over RT. And there, just a reminder that natural log of e to the x is simply just x. We had that one the other day. All right, so take this equation and just move it around just a tiny bit. Natural log of k is equal to minus EA over r, 1 over t, plus the natural log of a. And there we have got y, m, x, and b in this equation right there. And so natural log of the rate constant versus 1 over, now capital T is temperature, so T lowercase is time, capital T is temperature. And we're going to see both of them in the same equation in the same example pretty quick. That's why I did that. Natural log of K versus 1 over the temperature is linear. And of course, the slope of the line is EA over R. Next, we're going to hold A constant. and derive a combined rate constant equation for the Arrhenius equation. And I'll tell you now that the activation energy is independent of temperature. So back to this expression here. Oops. Okay, we're holding A constant, so A1 is equal to A2. This expression rearranges to give you A is equal to the rate constant K over e to the minus EA over RT. So taking that and substituting it in, what we get is that K1 over e to the minus EA over RT1 is equal to K2 over e to the minus EA over RT2. Rearranging just a tiny bit to get K1 over K2. I need more space than that. K1 over K2 is equal to e to the minus EA1 over EA, excuse me, over RT1 divided by e to the minus EA over RT2. E to the A over e to the B. How does that simplify someone else in class? You can type, you can talk. How does e to the A divided by e to the B simplify? Anyone? Yep. Good. Everyone's got it. Good. Excellent. I'm trying to encourage you to speak because most of the time you're going to get it right, and I'm not going to laugh if you don't, okay? This is trying to create a comfortable environment. But the answer that everybody is putting in there is e to the A minus B. So that means this becomes e to the minus EA over RT1 minus negative EA over RT2. Now we can start simplifying it by taking the natural log of everything. Now this bit in the middle is we don't need, we just need the front and the back. And you get natural log of K1 over K2 is equal to minus EA over RT1 plus EA over RT2. Realizing that EA and R are constant, are in both of those equations, we can simplify this one last time. Natural log of K1 over K2 is equal to EA over R, 1 over T2 minus 1 over T1. And that is the combined rate constant equation. Okay. And starting to boil over there. So before I do that last equation, let's go and look at that demonstration. So just give me a second while I need to hook it up and set it up. That's not. I just have to reset the camera because I had to unplug the USB. And to reset the camera, I just unhook it and hook it up. Now it's live. Unfortunately, that is the best I can do for temperature, and the water is just starting to boil on the left-hand side. So we've got these glow sticks that are sitting here in water. So what I want to do is I want to take 3 of them. This is water look. Yeah, that's fine. Take 3 of them and put them into the cold water. There we go. And I'm just going to move this over so everyone can see it. And take another 3 and put them into the hot water. Now, I'm just going to hold them to the front so people can see what's going on. And what you should be seeing is realize that the central beaker is at about 20 degrees Celsius, whereas the beaker on the left is at 100 degrees Celsius. And I'm trusting you're able to see the difference there. That's an 80-degree temperature difference, and it, at least in front of me, looks strikingly different. I'm just going to let go of that and go over here and grab these ones. Now, this one might be a little bit harder to see because it's going from 20 degrees Celsius down to 0 degrees Celsius, and it is a little bit dimmer. And there we've got it. I can see the difference in dimness here, but it may be challenging on the camera. But it should be fairly obvious that at 100 degrees Celsius, there is a substantial difference from 20 degrees Celsius. And that is due to more molecules having sufficient energy to overcome a barrier. We're going to be talking about that in just a few seconds. And I understand there's a few people that are on the Prince George campus right now. If you want to stop by, I am actually in Building 8, Room 421. So after class, if you want to stop by, you can have some glow sticks because right now I'm not going to use them for anything else. So they will be of use for you. If you want them, please feel free to stop by. I'll be here for about an hour after class is over. All right. The last thing I wanted to do is I wanted to look at this last equation right here. And I should be up now. Good. So I wanted to now determine the activation energy given that we were able to measure the half-life at 20 degrees Celsius and the half-life at 40 degrees Celsius. And this reaction is the one that we were looking at earlier. So just give me a second here. Just need to reset this thing. Apparently. There we go. Good. Good deal. The equation that we are going to be using is natural log of K1 over K2, is the one we just derived, is equal to EA over R, 1 over T2 minus 1 over T1. This is a two-state equation. We have state 1, given the data, is at 20 degrees Celsius. And at 20 degrees Celsius, the half-life, that's the symbol for half-life, T1 half, is 22.5 hours. And then we had state 2. State 2 is 40 degrees Celsius, and the half-life was 1.5 hours. We need to do a few changes to this, and just given the time, just as a reminder, the temperature needs to be in Kelvin. So T1, this is capital T1, is 293 Kelvin, and T2 is 313 Kelvin. And nowhere up here do we have the rate, do we have half-life, but we have the rate constant. And you were told in the question that this is a first order reaction. And in the first order reaction, T1 half is natural log of 2 over K. So you're able to go through and calculate K1 is equal to 0.0308 hours, and K2 is 0.462 hours. Now we take this data and this data and we substitute it in up here. Before I continue, I just want to point out that I arbitrarily assigned 1 and 2. It could have been 2 and 1. Not a problem at all. That would have worked. But if you need to verify that for yourself, I recommend that you go through and do this question both ways. Switching 1 and 2 to confirm that you actually get the same answer. And so after all is said and done, it's just a simple algebra problem at this point in time. You're going to get the activation energy of 103 kilojoules per mole. I'm going to finish by asking you which value of R do I need to use in order to, in this equation. Which value of R should I be using? Anyone? In Chem 100, you had gas laws, and you were introduced to several values of R. Which one do I need to use here? Why 8.314, William? Jada? I'll tell you, you are correct. You have the right value. It's 8.314, but why is it 8.314? And I thought the units on it would work, and that is exactly correct. Joules per mole Kelvin. The units are the ones that give you that determines which value of R you use. Okay, I want my activation energy to be in kilojoules per mole, so I'm going to use a value of R that has joules and moles in them such that they cancel, or that I get the correct units. And away we go. And that's where we're going to leave it for today. And when we come back, we're going to continue looking at this material, start looking at reaction mechanisms and the like. Does anyone have any questions? R is just a proportionality constant. It's commonly called the gas constant, and it has many different values that we end up using. Other values of R that are common are 0.08206. I'm just going to move over a little bit. Liters, atmospheres per mole Kelvin. 0.08314 liters bar per mole Kelvin. And there's easily another 4 or 5 that are used in different aspects of chemistry. And all that changes, of course, is the units that are associated with them. Okay. Now, Ty, do you remember the equation PV equals nRT? That's the R we're dealing with.
Okay, thanks.
Yep. Any other questions? Everyone's good? This actually makes sense? Justine asked the question about the course project. Your TAs would send you an email in this week sometime. I don't know if you have access to it, but the TAs will have your email address, and they will be contacting you to say, hey, I'm the TA that you're going to be working with this term. So once they do that, they will then be asking you for your course project topics, and the due date for that, just a reminder, is the 29th of January. You're welcome, Justine. Anyone else have any other questions? Okay, well, I've got 18 glow sticks up here. If anyone wants a few, please feel free to come up. I appreciate that. I'm just going to stop recording and